We want to solve the given degree 3 equation. We're asked to find all of the real and complex solutions. We also want to give the polynomial in factored form using complex numbers. We'll begin by determining the real rational solutions, or real rational zeros. One way to do this would be to list all the possible real rational zeros by listing out all of the factors of the constant term over the factors of the leading coefficient of 1, but instead we'll go ahead and just graph the related polynomial function and look for the x-intercepts. So what we'll do is graph y equals x cubed minus 5x squared minus 47x plus 259 and look for the x-intercepts, which will give us the x values that make the polynomial on the right side equal to 0. So here's the graph of the polynomial function. Notice we have one x-intercept here on the left, negative 7, 0. This indicates when x equals negative 7, y is equal to 0, which indicates negative 7 is a solution to the given polynomial equation. Let's go ahead and record negative 7 below as one of our solutions. This also indicates that x minus negative 7 or x plus 7 is a factor of the degree 3 polynomial on the right side, which means you can now write the equation as 0 equals, we'd have a factor of x plus 7, and the remaining factor would be a quadratic factor, which we'll now find by dividing x cubed minus 5x squared minus 47x plus 259 by x plus 7 using synthetic division. Remember, when using synthetic division, we use the solution of negative 7, not positive 7. So we first list negative 7, and then from here we are going to list out the coefficients of the polynomial on the right, which are 1, negative 5, negative 47, and then we also include the constant of 259. So again, we have 1, negative 5, negative 47, and 259. Remember, because x plus 7 is a factor, when we perform synthetic division with negative 7, the sum in the last column should be 0, indicating the remainder would be 0. To begin, we bring down the first coefficient of 1. Next, we multiply by negative 7. 1 times negative 7 is negative 7. Place negative 7 in the next column, and then we add and repeat the process. Negative 5 plus negative 7 is negative 12. Next, we multiply negative 12 and negative 7, which is positive 84, which goes in the next column. And then we add negative 47 plus 84 is 37. Multiplied by negative 7. 37 times negative 7 is negative 259. And notice the last sum is 0. This indicates the quadratic factor on the right is 1x squared minus 12x plus 37, or simply x squared minus 12x plus 37. And now to find the remaining solutions, because x squared minus 12x plus 37 doesn't factor, we'll have to use the quadratic formula. Recall the quadratic formula. In our case, where a equals 1, the coefficient of x squared, b equals negative 12, the coefficient of x, and c is the constant of 37. Performing substitution, we have x equals negative b is negative, negative 12, or the opposite of negative 12, plus or minus the square root of b squared is the square of negative 12, minus 4ac is minus 4 times 1 times 37, and all of this is divided by 2 times a, which is 2 times 1. Simplifying, we have x equals positive 12 plus or minus the square root of the square of negative 12 is 144, and then minus 4 times 1 times 37 is 148. All this is divided by 2, which gives us 12 plus or minus the square root of negative 4, all divided by 2. Recall the square root of negative 4 equals the square root of the product of 4 and negative 1. The square root of 4 is 2. The square root of negative 1 is I, giving us x equals 12 plus or minus 2i, all divided by 2. We need to be careful when simplifying here. We cannot just simplify the 12 and the 2 because we cannot simplify across addition or subtraction. Let's break this up into two parts. We have 12 divided by 2 plus or minus 2I divided by 2, which gives us 6 plus or minus I. So we have one real solution and two complex solutions, where one complex solution is 6 plus I, the other complex solution is 6 minus I. So now that we have our solutions, we can write the polynomial in factored form using complex numbers. Remember, each linear factor will be in the form of x minus the root or solution. So we already have the x plus 7 from x minus negative 7, which indicates for the complex solution of 6 plus I, we can write the factor as x minus the complex number 6 plus I, and the other factor would be x minus the other complex solution of 6 minus I. And we could remove the parentheses, but I'm going to go ahead and leave it in this form. So we found all three complex solutions, and we also wrote the polynomial in factored form using complex numbers. I hope you found this helpful.